So we actually going to do some trapezium rule, which is some really exciting stuff. And so he's going to do this, Mr. Giuseppe. He's the Pure Maths Unit 2 teacher and a student.
Let's kick it off one time, right? Same past paper, 2016, right? And we continuing on question 2. We're looking at part C here. And let's get straight into the dance one time, right? So we have let f of x, right, equal to this. You have this function here, right? For 2 is less than or equal to x, which is less than or equal to 5, right? Then they say, in the first part of part C, use the trapezium rule. So your mind should already be thinking, what is the trapezium rule? You should have that formula in your mind already, right? With 3 equal intervals to estimate the area bounded by f, the lines y is equal to 0, x is equal to 2, and x is equal to 5. So the first thing I am thinking is, what is the trapezium rule and the formula? So that's why I'll write down the general formula first of the trapezium rule. So we should have this here that they're seeing coming up, right? So we're looking at here the trapezium rule. So this is it here, right? And the next thing, the trapezium rule, we should know that basically the trapezium rule is just a bigger way, or it's another way of finding or estimating the area under the curve. We should all know this, right? We should learn off the formula, right? I always advise everybody learn off all the formulas. I don't think you have a formula sheet by which you could use in the exam, so learn off all the formulas. Even if it did have it, I wouldn't recommend they use formula sheets, learn off all the formulas, right? So this is the formula here, right? They say that basically when they say it's bounded by f, right? I just drawing up a little sketch of what it might look like. F would be this line here. Let's say some curve, right? Which would be this function there, right? And the lines y is equal to 0. Y is equal to 0 would be here, right? And then we have the lines x is equal to 2. This is x is equal to 2. And x is equal to 5, right? And basically it's this area here. This is your f of x, or your f, sorry, right? And we need to use the trapezium rule to find that area highlighted in red there, right? Or shaded in red there. That's basically what we're doing, and it's an estimate. It's not the exact value. So the next thing we have to do is we have to basically find out what these terms are, right? We have to do that. We have to find out what these terms are, right? And if, well, this is a general formula for the trapezium rule actually, right? So we wouldn't be using all of that. Now, right, we need to find out D. D is what? D represents the interval, right? It represents the intervals and the 3 equal intervals, and it tells you the size of the intervals. As I said before, the trapezium rule, or I think I said before, but if I didn't, the trapezium rule is basically a bigger way of representing the area of a trapezium, right? Which we normally know, or which we know is a half, right? The sum of the parallel sides by the height, right? So basically the trapezium rule, it employs that same principle, and we derive this formula, right? We need to find out what is D. How we find in D? The formula for D, we should know this. D is B minus A on N, where B and A represent the, and remember the diagram that I had before, right? This is your A here, or this is your x is equal to 2, and x is equal to 5, right? So A and a B are your upper and your lower limits, right? So that's basically what we need to put in there. And N represents the number of intervals, or the number of equal intervals. In some questions, we have to plug in your upper and lower limits here, right? That's what we need to do. And this is your lower limit, this is your upper limit, right? So when we plug in that, that would give us our value for D, right? 5 minus 2 on 3, and you would get 1. And that would be your D. That is the first thing you want to really find. Sometimes they tell you, they wouldn't say 3 equal intervals, they actually say ordinates, right? And you have to remember that the ordinates is always one more than the number of intervals. So if it was 4 ordinates they give you, you would really use you need to know that it's 3, right, equal intervals really and truly they're talking about. So this is 3 here, right? That's how you know what n is. N represents the number of intervals. So once you find d now, it's just a matter of finding out what these figures are, right, inside here, right? So those things, what we do is we need to find out the values of x, right, that we have. So what we will do here is this. We drop a table, right, because what happens with the trapezium rule, right? So we have the trapezium here, right? The trapezium rule, it breaks up the big interval that they want you to find the area under the curve for into smaller trapeziums, right? And in essence, the formula, it is basically fine. It's the sum of all these small trapeziums. That's basically what it is, right? So each interval, right? This is an interval here. This is an interval here, right? These are intervals here. You have, each one is size 1 unit, right? So that's why we start with your first, your lower limit, and we add 1 to it. We add 1 here again, and we add it, and you see it reach to 5. So that this would represent the first interval, this is your second interval, and this is your third interval. So that's your 3 intervals that you're referring to there. After, you need to just take each one of these x values, right? Each one of these and plug them into the function f of x. And then, well, basically when I plugged in 2 into the formula here, I got 11 on 5. Let me just try it really quickly with this, right? So everybody just look at the calculator here. We have, what is it? 2 is x, right? So you would have 2 squared plus 2 by 2, right? Plus 3 all on what? How do I go down? Right, so I get to there, all on, this would be 2 minus 1, right? Multiplied by 2 squared plus 1. 2 squared plus 1, and you press equal, and we get 11 on 5, right? So that's how you do it. Then again, for the next coordinate of x, we plug in 3, and this is what we will get. You do the same thing as 2, right? And you'll get 9 on 10 for 3, 9 on 17 for 4, and 19 on 5 for 5, and that's basically it. Right, so these are your values, and then we will rewrite the formula, right? This is just the general formula for the trapezium rule. We'll rewrite the formula so it would be applicable to this particular question here, right? We will rewrite the formula. So now let's look at it here. This is where we rewrite the formula and what we have here, right? So basically, right, we put the upper limit, right? Yes, the sum of the upper limit and the lower limit is what you have here, right? Well, f into the upper limit plus f into the lower limit, right? Or the lower limit into f and the lower limit into f as well. So basically that's where you're summing here. And then we multiply 2 by these 2 values here. That's basically what you're looking at there. And then this is what you would get. So just look at it here, right? This is what we have here up to this point, right? So basically what I would have done was substituted this here, and then these 2 here were substituted into this little area here, right? And well, multiplied by 2. So the key is really, this question is really about understanding the formula for sure, right? Remembering the formula and making sure you find D first. Find D first and you should be good, right? Understanding the intervals, right? And making sure that you find the correct D. After that, it's just a matter of, well, this is basically a solution here, right? But let's just tie up the question properly, you would get what the question asked for initially was the estimate of the area bounded by F. The lines y is equal to 0, x is equal to 2, and x is equal to 5, right? So you would get this here is like the exact value, right? And then this is basically like an estimate, and you just put units squared, right? Because it's an area and it's an estimate. The trapezium rule gives an estimate of the area under the curve, right? So that's basically it for this particular question, or this part of question 2 for 2016 trapezium rule. The key things, remember to learn of the formula for the trapezium rule, and also key thing is you deal with your D first, finding out what is the value of D, which is the length of each one of the intervals of each one of the trapeziums, right? And then it's just a matter of doing up this little table here, plugging in your values of x, right? Well, the upper limit would be, well, the lower limit is 2, right? And what you're doing is basically adding the interval increase, the amount that each interval is being increased by, which is D. And that's how you get these two values here, right? Take those x values, plug them into here, plug them into f, sorry, and this is f, that is a function. And then it's just a matter of substituting it into the formula and just plugging everything into a calculator, and you should get this as a solution here, or even this, right? If you're rounding off, and that's basically it. So let's move on now. Let's move on to the next part here, right? Let's move on to the next part, part 2. They say using partial fractions, show that f of x is equal to this here, right? So let's look at it, right? The saying required to show that f of x is equal to these two fractions, right? These two fractions here. So we have to show that. But recall what f of x was from the previous question, from part C, part I, right? Let's recall what it is. It is what? F of x was this big, right, rational fraction here, right? That function there. So partial fractions should come to mind. The first thing I do whenever I see partial fractions, I look at the denominator immediately, right? And the first thing I'm thinking is the denominator fully factorized? And yes, it is fully factorized. So that's good. The next thing now, I need to find out what are the corresponding fractions for each factor in the denominator. This is a linear factor, and then this is a quadratic factor in the denominator. Recall f of x is equal to this here, right? As I was saying, and we need to now indicate what are the corresponding fractions for each factor in the denominator. So let's go ahead and do that, right? So this is what we would get here. For the linear factor, which is this here, the corresponding fraction is of the form aon, right? Ax plus b. That's the general way, right? So in this case, it's just aon x minus 1. And then for the quadratic factor, this is the corresponding fraction. The general formula is normally, right, ax plus b on whatever is the quadratic factor below, right? So that's basically it. These are the corresponding fractions for each one of these factors, this one and then the other one there, respectively, right? Corresponding fraction for this, corresponding fraction for this. That's basically it. Now, what we need to do is find out what are the values of A, B, and C. That's where things get a little bit interesting. And what I like to do always is make this on this side here look just like this. So I would find the LCM, right? The LCM would be this multiplied by this, right? X minus 1 by x squared plus 1. That's the LCM. So I'll make it, bring this under one fraction, right? So this is what I would do next. Bring it under one fraction. And then I would equate the numerator, right? That's the next thing. Bring it under one fraction and equate the numerator. So that's what I did here. So if you notice, the denominators are the same, right? And they equal to each other. So the numerator should also to be the same. So I just equate the numerators, right? So that's basically what we're doing here. And that would help us now to find out what A, B, and C is, right? What we like to do, or what I like to do, is first, I like to look at the factors that we have here and see what values of x would cause them to turn to 0. And that is actually go a long way in taking off certain unknowns and leaving one unknown by itself, and you could solve for that one unknown. So this is what I'm saying here, right? When x is equal to 1, this is what we have happening, right? Why I use x is equal to 1? Because when you plug in x is equal to 1 here, it turns to 0. This would be 0. And 0 by this is 0. So it gets rid of this whole thing. When I put x is equal to 0 inside here, yes, it's 0, but 0 plus 1 here would give us 1. And 1 by a is a. So I get one unknown by itself. That's really good, right? And then, well, this on this side here, I plug in as well x is equal to 1, right? And what we see happening here is this. You get, when you plug in x is equal to 1 on the left-hand side, you get 6. When you plug it in on the right-hand side, you get 2a. And then when you solve for a, you get 3. So that's basically the method I would use. That is really cool. And then the next thing, what can we use next? We can use when x is equal to 0, right? That's our next one we could use as well. Because when x is equal to 0, this will turn to 0, this will turn to 0, this will turn to 0 and take off the b, right? So we just have a and c, but remember we found a in the first instance, right? So because we know what a is, we could just plug that in, and when we solve for c, we get 0. So that's cool as well. And then the last thing we need to do is find the value of b, right? Because we find a, we find c. Now we need to find the value of b, right? So what do? We can equate the coefficient of x. That's another way of approaching this question. You could have actually started off the question by equating the coefficient of x squared, x, and also to the constant, right? You could have done that as well. That's another approach that you could have taken, right? But here I'm just going to look at the coefficient of x. If you notice, a by anything here would not give you x, wouldn't give you any term in x, but b by -1 would give you a term in x, that would be negative bx, and then c by x would give you a term in x as well, that would be c. So therefore, the coefficient of the term in x on the left-hand side would be c minus b, right? Therefore, 2 would be equal to c minus b, right? What I'm saying is this here, right? Equating the coefficient of x would give you 2 is equal to c minus b, right? We know the value of c from the previous thing that we worked out. And then in the end, we get b is equal to -2 when we solve for b, right? So then the next thing, we just need to replace the values that we found for a and b into this here, right? And show that we actually get this. So what we would see is this, therefore, this is what we have happening, right? But let me just fix this here, because I have here plus -2x, right? But let's just change this. You could always just move this negative sign here, right here, right? And that is the same thing. This here is the same thing they have up here that they ask us to show, right? That's the same thing. So therefore, we see here our answer is correct, and we're good to go here, right? So that's how you do it with partial fractions. I always say the thought process is make sure that the denominator is fully factorized, right? Once it's fully factorized, the next thing to do, right? Well, actually, the first thing you should make sure that is not improper. That's actually the first thing, right? And that's looking at the degree of the numerator and the degree of the denominator, right? If they equal, or if the degree of the numerator is greater than the degree of the denominator, then it's improper and you would need to make it proper. Then you look to see whether or not the denominator is fully factorized and whatnot. And so if you're not doing pure maths unit 2, some of the things are speaking about maybe far-fetched and you might not understand it at all. But that's the first things you would look to do. I just putting in that there as a side note. And then after that, it's just making sure that you know the different fractions for each corresponding factor in the denominator. That's these denominators here, the corresponding fractions for each factor, right? That's key. And once you know that, you should be pretty good. And yeah, that's basically it. Right? Then they tie up the whole question here and asking, hence determine the value of the integral, right, from 2 to 5 of f of x, the same f of x, right? Just remember the f of x that we were dealing with, that rational fraction there with the quadratic and the two factors multiplying below, right? That's what we're working with again. So let's just look at this. This one's simple, actually. This real simple. So how would we do this? Let's just replace f of x with what it is, right? First things first. Let's replace it. We know f of x is equal to this here, that fraction there. And what I like to do always, well, so this is f of x from the previous question. We know that, right? So that's why I replace it with that. And also too, remember they say hence in the question. Hence usually is a big indicator that you need to use something from the previous question in this question, right? To solve this question, the question that we're currently in. So that's a big indicator, right? So that's why I use one time. This is my hence moment. This is the hence moment here. You you convert your partial fraction, right? Or you convert this big rational, complex rational looking fraction into the simpler two partial fractions that we found in the previous question. So that's what we have here. These two simpler, right? It's simpler to integrate, right? And that's what we do now is just integrate, right? So the next thing I would do though, right? Because I have two fractions here, I would use this rule for integration and I would just take each one separately, right? This is a big rule. You always use that, integrate, right? Separately, right? And then it's just a matter of these things looking pretty straightforward, right? Pretty straightforward here, right? Make sure you take out your negative sign out of the integration, right? The integral sign. And then it's just a matter of integrating 1 on x minus 1 and then 2x on x squared plus 1, right? The first one is pretty straightforward. It's just the ln of x minus 1 and it will be modulus as well, ln of the modulus of x minus 1 because you don't want to take any negative values, right? And then this one, if you look at this here, there's a real important integration rule here, right? It's the rule where you have the integral, right, of f prime of x on f of x with respect to dx. This is real important here, right? And this is what is going to be utilized here, this rule, right? And that rule says that the integral of that, if you have this function of a function of this form, it says that the integral is the ln of f of x, right? The modulus, right? The ln of the modulus of f of x, right? Plus c, but we don't need the plus c because this is definite integration, right? So basically, we'll be applying that rule here. So what you would have happening is, right, you would see something happening here. You have it here. This is your f of f. This is your f prime of x because x squared plus 1, the differential of x squared plus 1 is 2x, right? The 1 will turn to 0 when you differentiate the 1, right? So that's basically that. And then we integrate those two. So let's integrate them. When you integrate them, this is what we get in here, right? And you set up the dance nice. We could put the ln here as well, just to make sure that we take, the modulus sign here as well. I think I neglected to put that because you want to find the positive value of ln, right? And you will get undefined if you find the ln of negative value. Let me just check that real quick just to make sure. Let's check it where ln is on this calculator, right? Where negative is -2, right? So you get a math error, right? So the reason why they put the modulus there for ln, right? Whenever you find ln or the integral of ln, right, is because you want to always take the positive values, right? Because ln of a negative number would be undefined. So let me just clear this, right? And let's move it along really quickly, right? Remember to always have your limits here, right? That is key. Watch my setup real carefully as well, right? And then lastly, I'm just going to write out the whole solution here, right? So we're going to just look at this after, write it down, and that should be basically it for today, right? So let's look at it. So when you look at this here, what I basically did, remember, when you're looking at integrating the limits, right, or integrating any function with limits, right, your limits is 2 and 5, that's your lower and upper limits, right? You need to basically plug in your upper limit into the function and minus it from your lower limit. That's basically what is being done here. And basically, if you look at my solutions here, you would see I just kind of played around with the lons here. I would have added, well, this and this together, right, would come together. You could bring up the tree, bring the tree up here, so you would get ln of 4 to the power of 3, right? Remember that ln rule, and you would get ln of 64, and then we could actually bring the ln of 5 together with the ln of 64, and we know when we add ln, right, terms, you could multiply this by this, right? So that is what I did here, and I got ln of 320 minus ln of 26, and then you have a next ln rule, which says that you could take this and divide it by this, right? The 320 divided by 26. So that's basically what we did here. And then I just basically reduced it a bit. I just played around with this particular question with the ln and using the rules. And in the end, what did I get? When we integrate that, I got this. And something to note here, this is the exact value. This is the exact value. This is like an approximation of the exact value of the area under the curve, right? This is the same function being integrated, right, in the earlies. When we look at part 1, remember we use the trapezium rule, and we would have estimated the area under the same curve here, and we would have estimated it from 2 to 5. What answer did we get when we did that? Let me just go back. The answer we got was this. Watch it. 2.71. Remember, we said that the trapezium rule is an estimate of the area under the curve. When we did it using the integration, it's the same interval. We get 2.51. So you see, it's an estimated really close. The trapezium rule value that we got for the area under the curve using the trapezium rule is really close to the one we got using this is the exact way. When you integrate, right, you get the exact value, right? So it's very close to it. And in this case, they could throw in a question, or they could throw in the question and ask you whether or not the trapezium rule was an overestimate or underestimate of the area, right, under the curve. And in this case, it would be an overestimate, right? Because we're seeing that it's 2.71, right? I just looking at it, notice that, right, the trapezium rule would have given an overestimate of the area under the curve.